Hey AP Calculus students, this video is going to wrap up the remaining 3 related rates problems that we need to work through. So these are the ones that we ran out of time to finish on Thursday. And so we are in your blue notes, the ones that printed out with some of the rustic looking paper from the printer. So we were starting off with the isosceles right triangle problems. And with these ones, with the water trough, you should already have most of the schematic set up for example number 3 all set to go in your notes. So let's go ahead and reread the problem, and then you can pick up retaking those notes where you left off on Thursday. So with this example, it says a trough of water is 8 meters in length, and its ends are in the shape of isosceles triangles, whose width is 5 meters and height is 2 meters. If water is being pumped in at a constant rate of 6 meters cubed per second, then the first thing that it wants us to do is to draw a schematic of this scenario. So that means we just want to go back and create that picture that we had done in our notes when we first started this problem. So we're making a water trough here. And so that just means if we have an isosceles triangle with our water trough, that we can go ahead and label certain values based off of the problem setup and based off our knowledge of the geometric setup. So it tells us the trough is 8 meters in length, so that's going to be this value down here. And then it tells us the width is 5 meters, so this value right here, that's 5 meters. And then the height, so this value here, is 2 meters. So we have that information, that's our schematic, so we're good to go for setup there. So isosceles triangles just mean that these two values are going to have the same length. Then we get to go ahead and start on the related rates process. So it asks us at what rate is the height of the water changing. So height of the water changing means we're looking for dH/dt when the water has a height of 120 centimeters. Now notice this is asking us about 120 centimeters and the rest of the problem information was in meters. So watch out for little tricks like that can be easy to slip up on. We want to make sure we go ahead and change this value to 1.2 meters or that we change the other ones to centimeters. It's going to be a lot easier though to go with meters here. So ultimately the problem gave us information about change in terms of meters cubed. So we know that this is going to be a dV dt. So we have information about volume changing. We're trying to figure out information about height changing. So that means originally we're going to need an equation that relates volume to height. So let's look at this triangle shape over here. Our volume is going to be equal to the area of this triangle multiplied by the length. So we can say 1/2 width times height, that's just like our base times height, and then times the length gives us that third dimension that we need. But right now we have 4 different variables. We've got volume, width, height, and length. And we want to be relating 2 variables. That's our goal for this kind of problem. So the nice thing is that as soon as you fill in water in the trough, the length value is going to be constant. So we're not going to be condensing the trough in or expanding it out. So as we fill it up, the only thing that's changing is either our width or our height. So this value is going to stay constant at 8. So we can say volume equals 1/2 width times height times our length value, which is 8. At that point, we can multiply the 1/2 and the 8 together, and we can say volume is equal to 4 times our width times our height. And that looks a lot nicer because then we're just dealing with 3 variables instead of 4. But ultimately, we want to be relating volume to height directly. And so the issue here is that we need to substitute width so that it's representing a height value instead. Just like our cone problems, when we're dealing with these isosceles triangle trough type problems, the relationship between our width and our height is going to stay constant. So I can say that 5, my width, over 2, my height, is equal to width over height. And then that way I have a method of relating the 2 values. At this point, I can go ahead, let's rewrite 5 over 2 as 2.5. So I can say 2.5 equals width over height. And then I can multiply both sides by h and say that width is equal to 2.5h. At that point, I have a relationship between height and width, so I can go ahead and substitute down in here for the volume. So I can say volume equals 4 times, I'm going to replace this guy with 2.5h times h. Then I can just distribute in. So 4 times 2.5 is going to give me 10. H times h is going to give me h squared. At this point, I've got a method of relating my volume directly to my height, so I can go ahead and begin to use the related rates process. So we can say that dV dt, so how our volume changes over time, is equal to, I'm going to bring this guy out in front, so 20h dH dt. Now I was given dV dt in the problem, that's that 6 meters cubed per second. So we can substitute that in here for dV dt. We could say 6 meters cubed per second equals 20 times the height value that they gave us here is 1.2. And then we're solving for dH dt. So 20 times 1.2 is what I'm going to want to divide over. So I'll end up, this will become 24 if I multiply that in my calculator. And then I can divide both sides by 24. 6 over 24 is just 1 divided by 4. So this will become 0.25. And our units are going to be meters per second for our height value. So dH dt is going to be 0.25 meters per second. That's this value right here. So that's the process of solving for dH dt if we're given information about the volume and how it's changing over time. Now what we're going to find out is that part C is really just asking us to reverse this process for width instead of for height. So let's go ahead and set that up. From part B, we came up with the equation that volume is equal to 4 times W times H. That's that guy right there. And then we substituted in for W a relationship to get all H values, so all height values. We can do the same thing when we're trying to substitute in for H to only be working in width values. So if I were to come back here, we can just cross multiply real quick and say 5H equals 2W. And then if we're trying to get H by itself, we can divide by 5, divide by 5. So if we reverse the relationship, we have H equals 2/5 W. That's the same thing as saying H equals 0.4 W. So we can use that to substitute into this equation. So then we can say volume equals 4W times 0.4 W. So that's going to mean that volume is equal to, if I have 4 times 0.4, that will give me 1.6. And then I have a W times a W, so I have a W squared. At that point, I get to go ahead and repeat the differentiation process. So I'll have dV dt equals, if I bring this 2 out in front, I'll end up with 3.2 W dW dt. And then I can go ahead and substitute in my values. My dV dt was 6 meters cubed per second. And then I have 3.2 times, I don't have a value for width right now, so I actually have to go back one more time and substitute in the value for height to get a value for width. So if I do that, I can use either this expression or I can use this expression. Let's go ahead and use this one. So we'll have 2.5 times our height value, which is 1.2. That's going to give us our width. So if we go ahead and plug that in, 2.5 times 1.2, we get that our width value is equal to 3. So over here, we're going to substitute that in for W, and then that way we can solve for dW dt. So if we just divide this out, 3.2 times 3, that's going to give us 9.6. So we can divide by 9.6 over here. And if we plug that into our calculator, 6 divided by 9.6, we're going to get 0.625 meters per second is equal to the rate of change of our width over time. Now, that is a way of going about doing the width and the height completely separately and then substituting back in where necessary. There's actually one other technique we could have used to solve for part C. And that would come just as a quick overview. If we already found dH dt here, we could actually come just straight back to this relationship over here to solve for dw dt. Because look, we can say dh dt is equal to 0.4 dw dt. And then dh dt we found was that 0.25. So we can say 0.25 equals 0.4 dw dt. And then we can divide by 0.4, divide by 0.4. And if you take 0.25 and divide by 0.4, you also get out 0.625 as your rate of change for the width. So you have a couple of options when it comes to these multi-part related rates. If you have multiple equations that relate your variables, you probably will have more than one option for coming back to substitute things in. So this is the first application problem we wanted to come back to. We're next going to get into our angular measurement problems. So I'm going to pause this video and pick up on the next category for you to link to. Thank you, guys.